overview regarding CAE. CAE means computer aided engineering, which you will understand as we move further. And here you will come to know to learn like things like finite element, or maybe some words like meshing or boundary conditions. So you will be thoroughly go through these terminologies in these sessions. So here are some points. First, we will start from design validation. Then, how many ways are there? Like we can validate our design, and why there is a need of design validation. Even some analytical methods, numerical methods. Again, why we just follow numerical method? Why not analytical and experimental data or experimental methods? Again, some types of numerical methods. After that, what basically is computer aided engineering and why it is necessary in our industry life, I'll say, or day to day market scenes. And last, we will just compare. Like I heard from Ajay that you already have the session of SolidWorks, and so we will see at the end what is the difference between CAD and CAE. Okay, so starting with our first point today is design validation. Maybe anybody of you can tell me what is mean by design. Just you can unmute yourself and tell any one of you what is design. So you are from like mechatronics, mechanical department. So and that to second and third year. So can anybody tell me in one sentence or maybe two, three words what is design? So it's a base actually for learning the CAE. So if you know what is meant by design, so it might be anything. You can tell anything. So absolutely freehand. Anybody can tell what is design.
Making a basic shape and dimension for a model.
Okay, fine. Perfect. I can't see the name, but yeah, you said rightly. So just to know dimensions is nothing but my design. Fine, perfect. Again, along with dimension, we need to think of material also. So not only dimension, maybe my part is of plastic. So that is also one important point, like what material it should be, what dimension it should be. That's all coming under the category of design. Fine. So, what basically happens? Maybe I'll first explain the cycle. Maybe, for example, I'll take any example of maybe some beam. I'll say a simply supported beam. So, what it starts from scratch. Maybe someone like me, he will design first a beam. So, he will decide like what dimensions it will be and what material for that beam will be, and he will just make it or produce it or manufacture it. Then design validation means this step will come after my design. So I have now decided the dimensions, decided the material. In design validation, what I do, I check that dimension and material whether that can sustain whatever loading I have. So that is totally physical inputs. So whatever material I'm having, whatever dimensions I'm having, and whatever loads basically I'm having. So I will come on to this word loads after we proceed. So this is now clear what is design validation means, and this step come after the design, right? So here I'll just go through these statements. We can say design validation is the process to find out results like stresses, displacement, strain, fatigue, etc., which may or may not come on the model, which leads to failure. So what we took is a beam. I have designed it, and I have certain loads on that beam. Maybe a simply supported beam having a central load that I have designed, and now I'm validating it with the help of some computer softwares. And what results I get basically from that software is stresses, displacement, strains, and each of these component like stresses, displacement, strains, fatigue, eigenvalue, heat flux, they can fail that component. Means if I'm having beam and if my stresses are increasing in that beam, it may fail. If my deflection, I'll say deformation, if my deformation in the beam gets increasing, it will fail. If my strain goes on increasing, it will fail. So these all concerns are related to failure of my component. And what I do in validation, I just confirm that this should not cross my limit. Which limit for them for my material. And if this is not crossing the limit of my material, then I'll say whatever design I have made, it's perfect. And if it is crossing the limits, then I'll say it might fail, right? So this is nothing but design validation in overall. So let me just go, yeah, the same example has been explained over here. So design basically means what we decide over here is like length or dimension, maybe its cross section and its length. And secondly, again, you here we have some empirical formulas or maybe some equations available for some standard shapes, standard geometrical shapes, I will say. For example, here, if we consider it is a simply supported beam with the central load P, and that too at a center distance from two supports. So can anybody tell me like what will be the deflection at the central location? As you are studying in second year, you must know this, the equation of deflection. So what it will be? You can simply unmute yourself and tell me like what is the deflection of the beam in this middle location. Can anybody answer this? If no, then you can simply say no, we don't know it. But you should speak up. You should not like. So let me just go then. Maybe a serial wise. Yeah, Vetri, you can just tell me like if you know the equation to calculate this deflection, or you don't know. You can tell anyways. So no need to have. So everybody is here for learning. Vetri.
Hi, sir.
Yes, yes. Do you know like how we can calculate this deflection by using some formula?
Mm,
Okay, fine. Let me just go to the next slide. It is over there. So this is the deflection. What is my load into cube of my length, total length of beam divided by 48 into I. So I'll not go into the details of the each parts of this equation, but this is general equation of deflection for standard simply supported beam, right? You know now. So I can calculate by using this the deflection. Then now you will say me means if I am calculating this with the help of simple equation, then how why we need such computer softwares and all. So this is a a sure short question which will be coming into your mind. But let's take one example, maybe a great example of Howrah Bridge. So I assume that everybody knows the Howrah Bridge located in Kolkata. So it is one of the heritage of India. So what actually the Howrah Bridge is? It is nothing but simply a beam. What we are looking over here, like this, a simply supported beam. It is. So again, there are three methods to check this. Means three methods are there to validate my design. First is like analytical. We just talk about this. Like we have some empirical equations, that are in our textbooks. So by that, I can calculate deflection, stresses, strain, whatever I want to. Second is numerical one with the help of computer. I can calculate stresses, strain, and same things what we calculated earlier in this analytical method. Third is the experimental. Like in actual, I'll test that. I'll put some load on that component and I'll measure strains in that component, and I'll check what are the stresses coming and what is the exact deflection in my experiment. So these are the three methods by which I can validate if my design is good or not. So coming on to the now analytical one. So these analytical equations are based on certain fundamental or some certain assumptions basically. So maybe you might have heard this like material should be isotropic, means properties should be constant throughout my cross section. Second is like it should not have any, or you can say this material should be homogeneous, and we should not have cross section lag or difference in cross sections throughout my material. So these are some assumptions. Even load, it is acting at single point. So that are assumptions. But as we speak up of for the example of Howrah Bridge, consider that this is my Howrah Bridge, and one of the vehicle is traveling from that bridge with the heavy load. So maybe this vehicle is standing exactly at the center. Now I want to check whether that Howrah Bridge can sustain that weight of my vehicle, right? So how I can check? I have three ways. I can check with this equation. But to use this equation, whether this equation is applicable to Howrah Bridge, really it is applicable or not. So now the next number is Sudan. You can tell, means can I apply this equation to Howrah Bridge? Bridge is nothing but a beam, right? So can this equation, what we saw, can it be applied to Howrah Bridge to know the deflection of bridge? Yes. Just answer me in yes or no. So what do you think? Whatever it will be.
Yes, sir, we can apply.
We can. Okay. Okay. Up to some, we can apply it, but I'll tell why not. Because Howrah Bridge has maybe lots of speed breakers. It might have some speed breakers. That is one thing. Or maybe at some time some accident would have happened on that bridge. Maybe some railings, they might have broken out, right? That's why these assumptions are not fulfilling over here.
Okay, sir.
Yeah, maybe that Howrah Bridge have some holes, for some drainage holes in it, just to drain out the rainwater. Or maybe they have some, electricity board somewhere around, or electric lights they have. So which are not, under these assumptions, like my material should be homogeneous throughout, and it should not have any voids or any holes in between, right? So it is not as per my assumptions. So I cannot really calculate with the help of these equations, because whatever results I get will not be, accurate one. I can, but the results I will get at the end, they will not be accurate. That's why I need to go for numerical methods. In numerical methods, what I do, I simply model this Aura bridge with the help of SolidWorks or any 3D softwares, which you know now. And I create that holes, I create that speed breakers. If some accident would have happened, I just broke the railings outside. And whatever is the real situation, I model it in my 3D, I import it, and I solve it in some of the softwares. And the results I get, they are very much accurate. So as compared to analytical, now numerical results are most accurate in such cases. Third way to calculate this is experimental test. Now, I want to ask, experimental test means, as I already told, like we will put the weight and we will wait that when it will fail, and we will then calculate stresses, deflections, strains, and the failure. So that is the general experimental tests we conduct on the different materials. So now I want to ask Sri. I can't know the full name, but you can see like my cursor is there. So you can tell me whether this experimental test it's viable for this Howrah Bridge example. So can we do the experimental test, or the numerical method is good in this constant? Can you tell whether we perform this experimental or whether we go with numerical? Can you please unmute yourself?
Sir, in my point of view, numerical will be best.
Okay, okay. You great, nice, nice. Because just think, cost of building this Howrah Bridge, it might be a budget of one state for 1 year. So that much cost is required to build one Howrah Bridge, right? So in experiments, you just broke that. So that is not viable. In small pieces, it's good, but if you want to test a big or huge structure, it's not possible always. That's why these numerical methods are very good in terms. And yeah, nowadays, I would say this will be a future trend of every industry. All industries in the market, they are relying on these numerical methods and numerical validations. Again, here I have some pros and cons for all these three methods. Analytical, yeah, it gives me good results only when we what assumptions we have, we follow those assumptions. Only in that case. Otherwise, it's not trustworthy. Numerical methods, yeah, we have a lot of advantages. We can solve real life complicated problems, what we just saw, and results can be achieved faster. So as compared to experimental results, these results can be, we can find it in faster way. Even results can be achieved on like entire geometry. Like in this example, if I just go with this formula gives me result exactly at the center, not at this location or not at this location. For that I need to go for some other formulas. But if I go through these numerical methods, then I can see, I can point my cursor any location, and I can find out like what stresses, what strain is there. So that's that much simple. Even in experimental test, you can come to know results at one point. So at like some point apart from my loading area, it's difficult to get. You can get it, but it's little bit difficult, right? So that's overcome in these numerical methods. Again, even physical prototype is not available. In that case also, I can simply create a 3D model and I can test it. So I can do like this way. Even in experimental advantage of experimental test is, you will get 100% accurate results. Means after you do this test, then you must be a pretty confident that yeah, it will fail at this much load only. So that's one advantage of experimental test. But yeah, again, we have some drawbacks, like it's very much time consuming, and yeah, everything at the end comes to the cost. If you cannot bear the cost, you cannot go to that way, right? Yeah, so there are some advantages and disadvantages. You can also go through this if you like this afterwards. Again, now we will focus on these numerical methods. Again, there are some types of numerical methods by which we can calculate or we can validate our design. So there are four types we explained over here. First is finite element method, second is boundary element method, third is finite volume method, and last one is finite difference method. Finite element method means if we are using this method, we can say it as like finite element analysis. So in reality, so what happens over here? And now I have one question before going into this finite element method or analysis. I have one question for you. Can anybody tell me the equation of motion? What it will be? Equation of motion, or maybe a second law of Newton. So as you are young, you should know this, and you might have, you know, learned this in your 10th or 12th. Can you tell maybe the one, I can't see the name, but yeah, you can just tell me like what is the second law of Newton, or maybe equation of motion. Can you tell me? Can you unmute yourself, please? Or you can, if is not available. Can
Force
anybody
equals
tell? Mm-hmm.
The
Sir,
force is
mass
directly
into
equal
acceleration.
to rate of the
F is equal to mass.
Right. Force is equal to mass into acceleration. Nice, very good. Basically, this equation of Newton's second law, it is derived from my equation of motion. What my equation of motion tells me, maybe I'll just round it for you. Like force is equal to mass into acceleration plus k into x, means my stiffness into my deflection, plus c into x double dot, means whatever dampening factor I'm having into my velocity. So mx double dot plus kx plus c is general formula for my equation of motion. From that, it is derived that force is equal to mass into acceleration. So from that formula only, so this all finite element analysis is based on the simple equation of motion, what is nothing but F is equal to K into X. So here, what they have assumed, we do not have any acceleration, so that term got to zero, and we do not have any dampening, so that term also got to zero. So F is equal to, remaining term is only K into X, where K is the stiffness of my material and X is the deflection. So don't worry, we will go into the details afterwards. I just spoke up for this. So this is nothing but I just put this formula in the terms of partial differential equations. Why I need to do this, why I cannot solve with just a formula like force is equal to K into X, because in this finite element methods, I divide like whole model in small parts, and for that I need to make one matrix. That's why I converted my equation into partial differential equation, and I solved it, because my computer cannot solve simple equation, so it knows the language of only 0 1 and matrix language. That's why I converted my equation for the computer, right? And this method is known as finite element method. So got it? So any questions on this finite element method? So you understood like what equation is and what is happening. So it's clear for finite element method to all of you, because it's very important for our next whatever we need to go. It's clear? Yeah, you can freely speak up, means there is nothing to, can you tell me it's clear to you? Okay, fine. So here we have some inputs, and with that inputs we get something from that software. So in inputs we have loads, temperature, some certain constraints. So here I will be a little bit faster, because looking onto the time. So but it will be clear as we go on solving our assignments. So I have some inputs, basically loads, temperature, and constraints. So these are what in the language of computer aided engineering, I say this as boundary conditions, whatever inputs are there. And outputs in the terms of force, displacement, stress, strains, these are my outputs. So simply if I am having such type of geometry, if I am tightening any bolt, so what amount of stresses are coming in this region? So that's nothing but the solving of this finite element analysis. So load means at what load I can turn this to tight this bolt. So that is nothing but my load. Constraint is this one. So this bolt actually now it is fixed somewhere, right? So it is giving me some resistance while I am rotating this, while I am tightening this. So this is nothing but one constraint, right? So now coming on to the second method. So this is clear like finite element method. So this is my whole model. I have divided it in small parts, and then I have solved it. So this is nothing but my finite element method or finite element analysis. Second is boundary element method. In this, what I did, boundary element method, I just simply use the boundaries of my component or whatever design I have, and I calculate whatever properties I want, basically maybe vibration, stresses, or deformation, and I calculate it on my surfaces or faces basically. So same thing maybe explained over here is the most often used as an engineering design, similar to the more common finite element method. But BMA has distinction and advantage that only surfaces of domain need to be meshed. So here actually boundary conditions, as I said, they are a little bit different than the earlier. Here we have loads. They can be force, pressure, velocity, and acceleration. Even we can apply some vibrational factors in terms of frequency or maybe deflection, so that I can act as an input over here. In output I can get the effect of vibration, stresses, and deformation. So this is nothing but boundary element method. So basically you need to understand that boundary element method applies on surfaces, right? Third method is a finite volume method. So this is very important in terms of fluid dynamics. In computational fluid dynamics software, it is based on this finite volume method. What happens over here? In first, what we did, we just simply divided it in small part, and we calculated whatever it at single small points. I'll call it as node. Basically, this part is divided in number of elements. Okay, so let me just see. Okay, so this part is divided in some elements. I'll say it as element and nodes. I'll come on this when we will see the actual problems. But for time being, you just understand the difference between node and element. Element is the total part, maybe a triangular or a square, and node is a single point. And whatever calculations we did over here, they are on that point, which is nothing but node, right? Here we have the same thing happening in the volume. So whatever calculations are happening over here, they are on the volume. That's why this method is called as finite volume method. And this is basically used for fluid flows. Maybe you can so in this image you can clearly know that how the aerodynamic shape should be. So what is the resistance to the air by this car? So it has been we can see after we solve this using this equation, using this method. And again, this method is based on Navier-Stokes equation. So I'll not go in this equation right now, but just for your understanding, just to know you that finite element method is based on the equation of motion, and this computational fluid dynamics finite volume method, it's based on Navier-Stokes equation, right? Again, we have third last one, that finite difference method. Sometimes what happens, sometimes I need to check both, like I need to check the fluid flow like this. In addition to that, I need to check stresses coming into this car. So in such cases, means we cannot use this method separately, but yeah, there is one method, finite different method, which we can use it, which is a combination of both. Like here it might have explained, yeah, it is used in combination of FBM and FVM to solve thermal and CFD coupled problems together. So means in first we calculated stresses. So this is one method. Here we just checked the response like vibration, and here we have calculated the resistance, means the fluid flow basically. So these three different calculations we did, and in this finite volume difference method, we can combine two. Like I can see the resistance to flow or fluid flow, and I can also see the stresses coming into the body. Maybe here we have one example. Yeah, we have an example of this airflow along the aeroplane wing. So here I want to check how my airflow will be, and secondary, I need to check what stresses are coming onto this wing. So this I can do with the help of finite difference method. So until now, everything is clear to you, these four methods. So out of which the first is very important for our upcoming sessions. And yeah, these all methods have different streams. And yeah, you can look into that also afterwards. Now, coming into the CAE word, what actually is? CAE is basically computer aided engineering. We just had example of that Howrah Bridge, and why this CAE is necessary. Now you come to know why not only analytical, why not only experimental methods we can rely on. That's why we need this computer aided engineering. Again, it includes various analysis. So all these whatever methods we just saw, so everything comes under this computer aided engineering, right? So with the help of some softwares, we can solve these different methods. Again, we have, as I said, like we will see what is the difference between this CAE and CAD. So whatever you have done until now in SolidWorks comes under the CAD. CAD means computer aided design, right? So there you can either design a 3D part or 2D part or whatever it will be. So you can design it, and in CAE you can validate it. So that's the simple difference between two. Maybe we have yeah, again we have similar examples here. So CAE is about testing characteristics like material strength and fatigue by using engineering methods. So here we have the CAE model. So this is basically made by using SolidWorks, Creo, Katia, like that, 3D modeling softwares. Again, these numerical methods basically subdivided in 3 steps. You need to by heart now whatever I'm saying now. So these 3 steps are pre-processing, second step is processing, and third step is post-processing. So in pre-processing, what it comes in pre-processing, whatever I'm having in my CAD, it will come in my pre-processing, set up the model, I'll say. In processing, I have 2 steps, like I need to mesh it, means meshing is the first step in my processing. And again, second is application of load or application of boundary conditions. So this all comes in the step of processing. And my last step is post-processing. In post-processing, I'll understand results or I'll extract results. So these are simple 3 steps which you need to go while calculating this or while validating by using numerical method. So first one is pre-processing. In that you have a CAD model. In second one, you need to mesh it and apply boundary conditions. That is my processing. And third one is the post-processing. So you need to interact more with this CAD model and with these results. And whatever is in processing, like solving, means after meshing and applying boundary conditions, what will be in solving will be done by computer. So you do not need to take any headache. Just you need to give some inputs, you need to mesh it, and you need to just wait for some time, like computer will solve and it will give you this nice colorful results at the end. So I think this is it regarding the theory for today. So we will move on to one problem for today. But before going jump into that, I just need to take 1 or 2 questions, maybe. Have you understood like what where we have discussed until now? And anybody can tell, like, have you understood whatever we have seen until now? The one Vimal, I guess, right? I cannot actually unmute from my side. You can simply unmute yourself. Have you understood? Vimal, right? Hello? Am I audible?
Yes, sir, you're audible.
Okay. So have you understood like what we have just seen?
Yes, sir.
Okay, okay. So I'm waiting for response from him still, like I don't know. So yeah, don't shy. You can. Okay, okay, okay. Nice, nice, nice to hear you. Don't shy. And just one thing for you: just grab the opportunities whenever you get a chance to speak. Speak it out. So nothing will be, coming on to you. So you need to grab whatever opportunities are there. So yeah, now coming on to the assignment or maybe a session part. So I'll just brief you. So I'll explain you 2 problems today. So in first, please do not take or do not leave your attention from my problem. In second, you can just pinpoint some notes or something like that. So after 2 examples, you should be able to solve it by yourself. So just moving, we will be solving this problem of one cantilever beam having A into B, this cross section. So here are the measurements of my cantilever beam, and with the length and with some force. Like the length is this one, and force I am having 1000 Newton in the direction, in negative y direction basically. So we will be solving this by using Ansys. Just let me know, like everybody of you having you are having this Ansys installed, right? Hello. Uh, Everybody of you have this Ansys installed, right? Uh, can you please unmute yourself? I just want to know, means. Hmm?
Sir, not yet, sir.
Yes, sir.
Didn't install.
Okay. Okay. Some of you have installed it, but some of you haven't yet installed it, right?
Yes, sir.
Okay, those who haven't, they can try it. Today it's Saturday and tomorrow is Sunday, so you can try it installing. If you need any assistance, you can surely call Ajay. So he might help you in that. And yeah, so maybe for them who have installed it, they can just try it out like after this. Maybe the first part will be just to open the Ansys software. Just go into the search, type like workbench. So I have in mine it's 18.1. You might have 20 or 21. So current version in the market is 22 R1. So this is like a little bit older version I'm having. So this is similar, like whatever new versions are there, only some minor changes are there, and that's but it will be fine for us just to see what happens. So this is my project window. So as I just click on the workbench, just pay attention to the steps I'm following. So because you need to perform same steps and to calculate this. So just in the go to the search, put workbench and just open this. So this is my project window. Again, here I'm having a toolbox. In toolbox, I'm having different varieties of analysis systems. Again, I'm having some component systems. Below that, I'm having custom systems, and again design exploration and external connections. So the important menus from toolbox for us is this one, analysis system, and maybe afterwards custom systems. But this one is more important in terms of our calculation analysis systems. So go into analysis system and just search for static structural. So whatever we are learning today is related to this one, static structural. So just double click on this. So this is one way to open any analysis, or second way is just drag and drop, right? So by both ways, you can open this static structural window. Now I am deleting the other one. I don't need this, so I will just go with this one. Here I'm having certain steps. So engineering data, geometry, model, setup, solution, and results. So whatever comes in the geometry and engineering data, so second and third, it will come under the step of pre-processing. In model setup, it will come under the step of processing. Solution, it is also coming under the step of processing, but everything will be done by this computer, not by us. And in results, it is coming under the step of post processing. So we will be extracting results, like we will be seeing colorful plots or graphs in this. So first we will look in the engineering data. So we have this structural steel, a default material already defined. So we will, for time being, we will keep the material same. And I'll just right click on this geometry and I will open design modeler. There are again two ways by which you can do design modeler and space claim. So we will be going with design modeler now. So just right click on the geometry and click on the design modeler. So if you right click this and click on the design modeler, so that design modeler window should pop up. So this is very familiar like SolidWorks. So whatever you did in SolidWorks, that all things you can do over here in design modeler. So if you are like free to use SolidWorks, or then you can easily use this design modeler also, right? So here what you need to do, uh, you have like all the files. Maybe from SolidWorks you came to know that like how you can store the files in the form of step or in the form of IGS something. So that files directly you can import. What you need to do, you need to go in the files, import the external geometry, and maybe I can just import from for assignment one. Or no, basically here I think we have to this is a line body, so no need to import. We can just make this geometry in the design modeler itself. So basically what I need to do, I just need to go on to any 2D plane just to draw a line. So what I'll do, I'll just click on the XY plane and I will just click on sketching, right? So what I need to do, I need to draw this beam of length 500 millimeter. So what I will do, I'll select line. I'll just put my pointer here. Here I can see the P. P means it's nothing but a constraint. So I will start from that point and I'll put line. So H, it is coming H. H means horizontal constraints. So these constraints are popping up automatically. So you just need to click. So I'll click here. So I have drawn one line. And now before proceeding, I'll just check units, what units I have set. So here actually units are in meter. So I'll change it to millimeter. So whatever we have here is in millimeter. That's why I changed my units to millimeter. Now I'll go into the dimensions. So by default, this general dimension has selected. So I'll click on this line and I'll put one dimension. So here you can see the length. So what length I need, I'll just go in my problem statement and I'll see length should be 500 millimeters. So I'll just replace this with 500. So that's my length. And one more here, if you can right click and just make one square, it will zoom my object. Right click, drag, it will zoom my object. So this is nothing but 500 millimeter. So now I'm done with modeling a beam. Now I have to define its cross section. So what I need to do, I need to go in the concept. I need to go in the cross section. And which cross section we had? Rectangle. Let me show you again. The cross section is rectangle with the dimension A into B. So 60 into 98, they are my dimensions. So I have defined it rectangle, and here I have that dimension A into B. So I'll check over here. So B means this horizontal, H means this vertical. So I'll again come back. So A means vertical, B means horizontal. So A is 60 and B is 98. So vertical is 60 and horizontal is 98, right? So this is basically my beam. So I have defined now the cross section, right? Now what I need to do, so this is the only line diagram. I need to define it as beam. So what I'll do, I'll just go into the concept and I'll just make lines from sketches. So this is nothing but sketch at the moment. So I'm defining it as a beam now. So I have applied selected sketch one over here. Just right click and generate. So you can see over here now a line body. Right now I have defined this as a beam. Now I can define that beam a cross section. So cross section would be, so we have already selected the rectangle. We can just select over here rectangle. Now whatever this beam have, this beam should have this rectangle cross section, right? Now it's done. So we have prepared our model. So our beam is ready to test. So now just go onto the base window again, project window. Just click on this symbol. You will be back to my project window. Go into the model. So now we are done with the pre-processing step. Now we are going into second step of processing. Just double click or right click open, or maybe double click, both is working. Right click edit, or just simply double click on that. It will open my model window. Basically we call it as mechanical window. So first one is design modeler, we call it as like geometry window. Second one is model, we call it as like mechanical window. So it's opening. Yeah, here it is. So you can see two different windows, they are open. It's a design modeler and static structural mechanical window, right? So here you can see the geometry what we had earlier. Here you need to go onto the line body and you need to check. So in the detail window here, you need to check the material assignment, right? So this was the default material we have seen in engineering data, and now I have defined it as structural steel. Fine. So material is okay for me. I will check the cross section. This is a rectangle cross section with size you can see over here 98 into 60. That's fine. So this is correct cross section I'm having. So coordinate system, I will not go into this, and this is meshing. So what I will do, I will simply right click and generate mesh. So this whole part will be divided in small parts. So this is nothing but my beam. It is now divided in this much parts, right? Now, so now I have to define the boundary conditions. I'll just go and I'll check. So this end is fixed one, and this end I need to apply a force of 1000 Newton in negative y direction, right? So what I will do, first of all, I will just insert. So just go onto this tab, right click, insert, and say fixed support. Fixed support, right? Now, can you just go into this selection? Again, I just forgot to tell you. So these are all the menus. Maybe I'll say toolbox. So from that, you can simply pick whatever you want. So this is just for selection, a single point or box select. Again, this is selection for vertex, edge, or face. This is actually, we do not have any 3D model, or you can select body also over here. From here, you can select node elements. Even here, there again some options. You can simply see these options. You can play with some certain options afterwards. So for time being, what I'll do, I'll just select vertex over here, and I'll put this and I'll apply this. So what I did, I have applied fixed support on this vertex, right? Now on this, what I'm having a load of 1000 Newton in vertically downward direction. So what I'll do, I'll simply insert a force. Force at what location? At this location. And my direction is negative y. So what I will see over here, defined by vector. Instead of vector, what I'll do, I'll see components. And in components, I have to define 1000 in y-axis direction. So I'll put y and 1000. So you can see the force, right? Now I have the fixed support, and I have the, at this end I am having fixed support, and at this end I am having a force of 1000 Newton. Now before solving, what output I will be having, what outputs I need, that I need to check. What I need to have, I need to have a stress, and I need to have deformation, right? So I'll simply go on solutions, and I'll say I want beam section results, because if I can't select this as a S, it will not give me results for stresses. So I just need to make it on, so that I can get stresses along the cross section, right? So my point is here. So my processing part is done, I'll say. So only part remaining is solving. So I'll right click and solve, or I have one more option, just go here and click on solve. So by both ways, my analysis will solve, and only now computer will take its time to solve, and afterwards you can see the results. Okay, so now it has done solving by this end. Now what I have to do, I have to go in the post processing. In that, I need to add certain results. So I'll just click on this solution part. So these windows will pop up. In that, I need to add stress. I'll say equivalent stress, my first one. Or what you can do, same thing you can add by right clicking. Right click, insert, stress, equivalent stress, right? So now one is equivalent stress, second is deformation. I want to check deformation. So I will insert deformation or total deformation. Again, I'll right click, insert deformation, directional deformation. So which direction I want? So this is my beam in X direction, and I'm having load in Y direction. So directional deformation I want in Y direction, right? Because in Y direction I am having a load. I'll simply right click on this, and I'll say evaluate. I'll get this nice colorful results. So this end is fixed, and this end I have applied load of 1000 Newton. So these are my equivalent stresses generated. And now you can see at any point you can extract the results. Maybe here you just need to go on this probe, and if you just move your cursor, you can come to know what the results are. At any point you can take the results, right? Again, going on to the directional deformation, you can see the maximum deformation is 0.045, that too at this end. So it's in negative because y positive is in upward direction, so it is deforming in downward direction, that's why it is saying negative, right? So that is the maximum deformation happening in this beam. So this is it for the first problem. Now we will be moving to the second problem, and here I will be a little bit faster now. And yeah, I'll be solving same problem for circular cross section now. If you want to take some notes, you can take in this, because second time I'll be doing everything again. So starting from scratch, I'll take one static structural window. So there I have to calculate for circular cross section. Here also you can rename also. So what I'll put problem number 2. This is my problem number 2. Again, I'll simply check which material we want. So now it's aluminum alloy. So in previous example, we have used structural steel, which was default. Now I have to go for aluminum alloy. What I'll do, so here I am having engineering data sources. It's a material library of Ansys. So I will just need to click on this engineering data sources. So here I am having n number of materials, out of which I need to select general materials. So all these materials like steel, aluminum, all these materials are coming under this general materials category. So from that, I need to select aluminum. So here is aluminum alloy. I just need to click on this plus symbol. If I click on this plus symbol, you can see some symbol in this column, means this material has been added into your library, into your current project library. So again, I have to click on this, so my original window will come up. So this is the aluminum alloy, it has been added over here. So now again, go back to my project window. And now what we did earlier, we have, after defining the material, I have to go for geometry. So now again, I will open one design modeler window. So in design modeler window, I will create the model. So the model is this one, having 400 millimeter length, right? And the cross section diameter is 66 millimeter. So I'll go on sketching. Now you can just look on to my steps. I will put line, a point, and length. Then dimensions, general dimension by default, select. So size is, see, the unit is in meter. You can see from here or here. I do not want it in meter. I just go in the units. I'll set it to millimeters and I'll set it to 400. I'll zoom it, right click, drag. So this is 400 millimeters. So this is done. Now I have to define its cross section and I have to define it as a beam. So first of all, I can define it as a beam, or I can define cross section also. So anyway I can go. So now I have a circular cross section, that too with the, here you can see this is radius, not a diameter, right? R. Oh, they have mentioned it R, but yeah, it's a diameter, not radius. See, it's a 10 millimeters. So what we will be requiring is 66. So I'll just put 66. So this is nothing but 66 millimeter diameter circle. Okay, now I have to define the line. So lines from sketches. So which sketch? Sketch number 1. Apply and generate. So now this beam is created, and I just need to apply a cross section for that beam, which we have already defined here, right? Click circular. Now I have that circular shape cross section. Now what I need to do, I need to go back to the project window. I need to double click on the model or right click edit anything can work over here. With that, I'll go into the mechanical, right? Mechanical window will pop up. So I have this sketch. I am again back into the design modeler. I need to go with the mechanical window, this one. So I just check over here whether I have the same geometry. I have the material structural steel, but now we have the material as aluminum alloy. We have already defined it in engineering data. Now I need to assign. What I'll do, I'll simply click on this drop down. Here I am having that aluminum alloy. So I'll click it. So my material is aluminum alloy, right? Now, I need to check the cross section, whether which cross section we have over here. So circular one with a diameter of 66 millimeter. So that's fine. So this is exactly what we will be requiring. So now in meshing, just right click and say generate mesh. So it will mesh C. So actually this is a circular one, but because of this mesh, we can see like a non-circular part. So I, for time being, we will just keep it as it is, and we will solve it. We will now see. So this end is my fixed one, and force will be my 3000 Newton. So now in this structural window, right click, insert, force. Force, I have to select the point or vertex. I need to select it here. So the force is in the Z direction. I have to select it here, component Z in negative Z direction, 3000 Newton, right? Now I have to apply a fixed support. Insert, right click, insert fixed support at the vertex, this one. So this is fixed. Now what results I want? I want its equivalent stress, and I want deformation. So I want equivalent stress. That's why I just make it on. Otherwise, I will not get the equivalent stress results. And I just right click and say solve. Right, so it has solved now. So just right click, insert stress, equivalent stress, right click, insert deformation, directional deformation. Which direction? Z direction. Here also you can double click, or you can simply click on this drop down, and you can select from that Z axis. So from Z axis, because we have force in Z axis, right click, evaluate. Nice, you have this nice colorful result. So you can also put some probes. Just click on this probe. You can just point it out here, here, or somewhere here. So these are the results. So I think yes, we have solved second problem also. So again, now you can try by yourself to solve problem 3, 4, 5 onwards. So you just, what you just need to do, you just need to change this cross section. Just go in this one, cross sections, and here all the cross sections are available. You just need to select them. Can you do this now? As we have solved two problems, for third one, can you try this? So in third one we have, yeah, hollow cross section, hollow square tube, I'll say. So maybe I'll be back to my. So have you understood? Everybody, please unmute yourself. So we are to the end of the today's session. So please unmute yourself. And if you have any question, you can ask now. Am I audible? Please unmute yourself. Okay, kindly unmute, all of you. And if anybody has any background, then for him or her, it's fine. Uh, so you understood whatever we have seen today?
Yes, sir.
Okay, nice,
Yes,
nice.
sir.
So now you can try for this problem 3, 4, 5, means problem 3 onwards, you can try by yourself. Those who have Ansys installed, surely they can try, right? Hello?
Yes, sir.
Please be in unmute mode. Don't mute yourself now because we are into the end of the session. So you just try it first, second, third, at least first 3 examples you should solve. I'll ask on Monday who have solved this, and those who do not have Ansys, those please get it installed. And if you need any assistance, yeah, you can surely call Ajay and get it done. Right?
Yes, sir.
Okay. So you all of you have these uh, PDFs available with you, right, or not? Is
No, sir.
this no? Just a moment. Ajay, are you here? Okay. Maybe. Can I put it over here? Let me check. Please be on unmute mode. Don't mute now. It's fine. No, I cannot put actually the file in this chat box also. I'll ask Ajay to send this to all of you. Okay. He will share this 2 PDFs basically, and we are interested in now this one, assignment number 1. So problem 1 we have solved, even problem 2 also we have solved. Now what I asked you just to try with this problem 3 and 4. Just but before that calculate 1 and 2 again, and afterwards 3 and 4 you should try by yourself. By Monday, those who have Ansys installed, those can calculate this or be prepared with these 4 models, and those who do not have Ansys, get it installed and try this. Hmm? Any questions anybody have? So if they have any questions, you can ask, or if not, then yeah, we will stop maybe in next 2-3 minutes. So it's open to you. Do anybody have any question? So maybe you have question, you do not have question if you understood everything, or you do not understood anything. So in these two scenarios only you do not have questions. If you are in between, then please ask the question. So I assume that everything has understood, right? Is it?
Yes, sir.
Okay, great to hear. Okay, then we stop here for a day, and yeah, let's see you again on Monday. So before that, be prepared. Just go through this session, and I'll ask Ajay to share this assignment number 1 with you. If he hasn't shared yet. Fine then. Yeah, I wish you a nice day. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.